week 9. As usual, you have reading quizzes due Thursday, graded assignments due Friday, and something fun for this coming Friday, a nice little assignment special for 4.3. 4.1 is on the basics of differential equations. Hey, that's a nice word, equation. An equation is involving an equal sign. On one side, you have an expression. On the other side, you have an equivalent expression. The equation becomes a differential equation if it involves a derivative. In calculus, you study derivatives. Derivatives is a rate of change. When you have something like a polynomial, here's a nice polynomial. This polynomial is quadratic. If you were to throw away the very first term, you'd be left with a linear polynomial. If you throw away both the first and the second term, you're left with a constant. Other ways to say the same thing is that this polynomial is degree 2. A linear polynomial is degree 1. A constant polynomial is degree 0. A similar notion of grading, separating, identifying differential equations is the notion of order. And just like the degree of a polynomial is just looking for the highest power, the notion of order is looking for the highest derivative count. So no derivatives over here, no derivative there. Oh, just one derivative. The differential equation given in A is of order 1. For B, here's 3 derivatives, 2 derivatives, 1 derivative. The order is 3. 4 derivatives, 2 derivatives, 0 derivatives, 0 derivatives. The order is 4. Very straightforward. To solve a differential equation, you will integrate. Anytime you go about integrating, you know that you need to come up with an antiderivative, but then a constant of integration. Any constant is good because a derivative of a constant is 0. So all of these here, parabolas with different values for c, different constants added on, solve some given differential equation. They all solve a differential equation. This is a family of solutions. Each one is a general solution. Each one takes the form of y squared plus constant. Now, if you were to pick any one of these c values, you would then have identified a particular solution. The way in which you go about doing that is you're presented with a problem. So here is an equation, which happens to be a differential equation, which is setting up a problem. On the left-hand side, you're looking for an unknown function, where if you double that function and add its derivative, you'll get this nice expression on the right-hand side. What is the function? Well, the idea is, in this chapter, you're going to learn 2 different ways for doing that. We'll get to that in a second. The main way of solving is you'd like to just integrate. When you integrate, you pick up a constant. That gives you a family of solutions, which is called a general solution. When you pick something from that family, then you have identified a particular solution. How do you pick? Well, that's given in this equation here, which is the initial value. You want your unknown function at this particular input to have that particular output. This will then fix that arbitrary constant of integration, hence giving you a particular solution. Okay, do a simple example. This is 38 from 4.1. Here is the problem. dy dt is twice t. Restated that in a nice way. Y prime equals 2t. Integrate on both sides. When you integrate, y prime will turn into y. 2t will turn into t squared. And then you know this is an indefinite integral. You pick up a constant of integration, giving you a nice family of solutions. This here is the general solution. Next, when you look at this particular initial value, you simply plug in 1 for y, plug in 0 for t, and then find that c must be 1. Come back and write down, aha, I have my particular solution. I have a solution to the given initial value. Same thing for the other guy. And here are those two solution curves plotted together, and that would correspond with this one and with this one. Now, Desmos is very, very helpful, very, very friendly. Follow this link, and you'll see that you have different input fields already filled out. Take a look at this first one. It says a derivative of y with respect to x is set equal to some expression involving both x and y. In the second input field, we can dictate how we want to define that g of xy. And in the example, we're just going to take twice x for g. Then looking at the plot that it produces, you'll see something that looks like this. They're nice color-coded. All of the orange guys are occurring at some particular y value. These orange guys are occurring at some different y value. Now look at x values. If you take any of these x values, those are going to be negative valued, and all of these lines are of a slope which is negative. Take those line segments which are occurring on the y-axis, they all have a slope which is equal to 0, which is exactly the x value. Take any x value over here, which is positive, and then all of these slopes are positive. This is the idea of a slope field. Let's do an example. Newton's law. Hey, today is a wonderful day. It's 72 degrees out. Everywhere, all day long, nice and controlled, 72 degrees. If you take an object and you look at the object and you figure out its temperature, your body, maybe an ice cream cone, maybe a hot cup of coffee. Look at the temperature. That's capital T. Now watch how the temperature of that object changes. Take the ice cream cone. Here is 72 degrees. If the temperature is 72 degrees, 72 minus 72 is 0, then that change will be 0. The change of that object will be 0. Take the ice cream cone. The ice cream cone is going to be of a temperature which is less than 72. But the ice cream cone is going to absorb some of that heat from its ambient space, and the temperature will rise as time goes on. Take the cup of coffee. The cup of coffee is going to start with a temperature which is greater than the ambient temperature. The cup of coffee is going to then be losing its heat, giving off its heat to the ambient space, and it will lose its temperature. Okay, so what we have here are two different solution curves depending on what we wanted to assume that we're starting with the initial temperature. Is it less than the ambient space? Is it more than the ambient space? And when looking at these solution curves, you should notice that they follow the shape of an exponential function. This is Newton's law of cooling. This is your assignment. Update the Desmos link by plugging in this g of xy. That's the first thing. Then produce an image of that slope field. It should look something like this minus that solution curve. That's part 1. Part 2, go and read up on separable equations. Learn how to separate variables. Use that technique to solve this equation. That will give you a general solution. Next, that constant of integration c, fix its value by plugging in for x, -8, plugging in for y, 0. That's part 2. Part 3 is to now go back to Desmos and plot the solution curve like I've done here, but this is done for the solution with initial value y of 2 equals -4. Lastly, use the week 9 assignment form and paste here that slope field that you produced in Desmos. Paste here your handwritten work to solve the initial value problem. And then paste here the updated slope field produced in Desmos that has your particular solution.